Okay, in this T2 example, we're going to look to see how to use a sampling distribution to do some calculations. And so suppose we have the following scenario. Suppose that we use some U.S. Census Bureau data on household income from a large metropolitan statistical area in the year 2003. And suppose that we discover that the household income on average for the entire metropolitan area, let's assume that that's the population, was $76,089 with a standard deviation of $27,839. Now, suppose that we took a random sample of 100 households from the metro area and we calculated the mean income of that sample. What would be the probability that the sample mean is between 70,000 and 80,000? Okay, now to answer this question, we basically have to use what we know based on the central limit theorem. And we know that if we took all samples of size 100, the sampling distribution would follow a normal distribution. And that's true if we have a large enough sample size, that is anything above 30. And since we have a sample of 100, we certainly have that. And so we also know that the population mean is going to be 76,089. So that's going to be at the center of our distribution. And so if we graphed the distribution of all possible sample means of size 100 drawn from that same population, we know that the middle value is 76,089. And in this question, we're trying to figure out the probability that the sample mean, based on a sample of 100 households, is between 70,000 and 80,000. And so that's going to represent the area basically right in here. So in order to answer this question, what we have to do is we have to take 70,000 and we have to turn it into a z-score, and we have to find the area under the normal curve corresponding to that value. And since 70,000 is less than our mean, that's going to be an area below the mean. We also have to do the same thing for 80,000. We have to take 80,000, turn it into a z-score, and figure out the area corresponding to it. And since that's above the mean, we're looking for this area. And then just have to add those two areas together, that is this area plus this area, and that'll give us the area that we're looking for. So let's look at the calculations. We're going to use this formula. The formula tells us to take some value, in this case y bar, and subtract it from its mean, mu sub y, which is the population mean. And we divide that by sigma sub y bar, which is the standard error of the mean. Now notice that this formula is a little bit different than the one we used previously. Last time what we had was a normally distributed variable. This time what we have is a distribution of sample statistics. And so if we assume that the average income can be represented by the Roman numeral y, this time we have a distribution of sample means. And they're distributed around the value of the true population mean, 76,089. And then we divide that by the standard error of the mean. And remember, the standard error of the mean is equal to the true population standard deviation, sigma sub y, divided by the square root of the sample size. And that's true because as we increase the sample size, we have less variation in the sampling distribution. So we need to account for that. So here's the formula that we're going to use. Our z-score is going to be equal to the sample mean minus the true population mean divided by the true population standard deviation divided by the square root of n, or the standard error. And so let's start with our calculation of the standard error. Remember that the true population standard deviation is 27,839. And we have a sample size of 100. So if we take the square root of 100, we get 10. And if we divide our true population standard deviation by 10, we're left with 2,783.9. Now, we can start by calculating our first z-score, the one for 70. And so to calculate that, we would take our sample mean, 70,000, subtract the true population mean, 76,089, and we divide it by our standard error, 27,083.9. And when we do the arithmetic, we get a value of negative 2.19. Now, negative 2.19 is not going to be listed in our standard normal table, so we're going to have to look up the positive value in the table. But we have to figure out which column we should look at. Do we want the area between the mean and the z-score, or do we want the area beyond the z-score? So if we're looking for this area, we're looking for the area between the mean and the z-score. That's going to be column B in the table. We don't want the area beyond the z-score, which would be this area here. So that would be column C. So we're going to look at column B to find the area that we want. So we're going to look up negative 2.19. Remember, negative numbers aren't listed because the curve is symmetrical. And so only positive values are listed. But the area between the mean and the positive z-score is the same as the area between the mean and the negative z-score. So we're going to use this value, column B, and that's equal to 0.4857. And so there's about a 48.5%, 49% if we round, chance of getting a sample mean of 70,000. Well, what about the other side of the equation? What about 80,000? So we can do the same thing. We can take 80,000, our sample mean, subtract the true population mean, 76,089, and we divide that by the standard error of the mean, 2,783.9. And when we do the arithmetic, we get a value of 1.40. So that tells us that 80,000 is 1.4 standard errors above the mean. And so again, we're going to have to look up 1.40 in column A of our table. And then we're going to look up the column B value, which tells us the area between that value and the sample mean. And so that turns out to be 0.4192. And that tells us basically that there's about a 42% chance of getting a sample mean of 80,000. And so we just have to add those two areas together. So 0.4857 plus 0.4192 gives us a total value of 0.9049. And basically that's the answer to our question. We see that the probability of finding a sample mean between 70,000 and 80,000 is about 0.9 or 90% chance. So it's quite high.